density. We're going to start not with these, but we're going to start with some solutions we've made up already. Some 0% sugar solution, well, that'd be water. And we've got 5%, 10%, 15, and 20. And the very first thing you notice is they're colored. That's just to help the students keep track of them. They're also in labeled cups. That's just a little bit of food coloring, too little to have any influence on the density. One of the things this lab also does, along with tying in density and sugar concentration, it teaches a nice technique, that is how to use a volumetric pipetting, not by mouth either. I know these are all things that could be consumed, but that's not done in the lab. So we're using a pipette bulb. And we're placing a 100 ml beaker on the scale and zeroing it, okay? Pushing the tare button. So the scale right now, of course, reads 0.00. And we're going to first create a little vacuum in there. And I'm going to draw up into this pipette. It sits on the bottom, by the way. That's what blocks. You have to lift a little bit off the bottom. And well, I'm just about there. I got a little bubble there. And now I'm going to use this to bring it down. Oh, perfect. Okay. And the technique involves then coming over here. Make sure you push this button, not this one here. And I'm releasing that 10. And that is a very precise 10. 10.00 milliliters. Seriously, 4 significant figures on that. And why is this so much more precise than a graduated cylinder or a syringe or something like that? Look at the shape of the volumetric pipette. Right, I'm going to let this drain out first here. And then the technique is to actually touch the last drop to it. And this little bit that's left in there is meant to be left in there. And that 10 milliliters of water, you're thinking 10 grams, but not quite. It's 9.98. We'll have that recorded over here on the board. 9.98. Generally, that comes out to be 9.94, 9.95, 9.98. Less than 10, because 10, that's a density of 1. This is 10 milliliters. That would be only true at 4 degrees Celsius. So this is actually showing us that at room temperature, that water is a little less dense. Its density would obviously be 0.998. Rather than empty that out, the nice thing is we simply re-zero it each time and just add the next solution to it. But as I'm filling this up this next time, the reason this is so precise is because the increment is on such a skinny part of the pipette. The increment's not here. It wouldn't be as precise then. It's there. This is so it can hold 10 milliliters, but that line indicates the level of precision. Okay? So now we're filling it up with the 5%, and this has sugar in it. Okay? 5 grams per 100 grams of solution. It's 5% by mass. And now we're trying to let out just a little bit. I don't know if you can zoom in on that meniscus there, but ideally you would have it going up and down so that that meniscus is just sitting on top like that. Okay? Takes a little practice to get that technique down, and that's something the students can learn. Of course, it's a little old-fashioned, these pipettes. Now they went to work in a lab. I don't think they'd necessarily be using these kind of pipettes. They've got these ones that are done automatically, electronic ones. But I'm now letting this 10 mils of 5% solution into the balance here, into the balance. It was zeroed, so this is just telling me the mass of the added 5% with that little drop there. And we're looking at 10.15, okay, 10.15. And we're just going to go right along. I'm going to zero this. And what we're doing here is we're generating a standardized curve. Okay? That was an easy one. And I wish I had a camera on this scale to keep me honest, but these are the actual readings coming off this scale. I'm not making these up. And we're going to plot that data, draw a best fit line, and then use that to determine the sugar content of these various beverages. Okay? Here's our 10%. Get the last drop off there. You can make a prediction what that would be. It's 10.34. Okay? I need to get a little bit more air out of the bulb there. Just 2 more to do here, and then we're going to plot our curve. Okay. I could have done this all ahead of time and just written down the data, but I think it's more important you see this thing does work. Okay, here's our 15%. And you know what I forgot to do that time? I forgot to zero it. That's okay, because we know what the last one weighed. I'm just going to subtract it. Okay? It certainly isn't as though I have to start all over again. Right now the scale is saying, it's not saying anything, but it's showing 20.94, sorry, 95. So if we subtract out, we get 10.61. Okay, good enough. And I will zero it here so I don't forget. And the last one we'll do here is the 20% sugar water. It gets noticeably more viscous with this high sugar concentration. Okay. And there we go. It's been zeroed. I remember this time. You get some nice little color changes taking place in that beaker, but that's kind of irrelevant. Not a chemical reaction, just a physical process as they mix. They mix so well because I keep on putting the denser one on top. If I'd gone in the other order, I'd probably have a nice little density gradient rainbow in there. And this last one now, that last dropout, that drop does show up as a couple extra. 10.78. Okay? So let's just see what that looks like as a relationship here. I think if I move these cups out of here, we'll lose that shadow. Okay? We have, I'm just going to take those values off the board and divide them by 10, which I can do in my head. Don't need a calculator for that. So our first one, 0%, is 0.998. So we go up to here at 0 and put a little dot here at 0.998. Our 5% is 1.015. So 5% up to open right here. Okay, hey, so far that's a pretty good linear relationship, isn't it? That was a joke. It was two lines, two dots. Okay, the next one is 1.034. So I'm going to right here, I believe. Not often I have to graph things upside down. Now you are seeing, though, some nice data. That's pretty linear there. 15% is 1.061. Okay, and then the 20% is 1.078. Okay, I think I did that right, yes? Okay, just going to lay this down here and draw a best fit line and know that the data is not going to be perfect, but, whoop, my ruler slid, sorry about that. Here we go. Ignore this one. Now we have a standardized plot. What can we use that for? Well, let's go to our beverages here and swap them out. Let's try Gatorade first. Okay. We don't even have to empty that beaker yet. We still have room there to zero it. Drop some Gatorade. You can make your predictions where it's going to be. And not only can you tell the hierarchy, which one's the highest sugar content, you can get a value for that concentration of sugar. How many grams of sugar dissolved per 100 grams of the beverage? Okay. And our Gatorade, you want to make an extra line there or off to the side maybe? Gatorade. Now we chose this range of sugar concentrations because it covers the whole range of these beverages. So we're really going to be just doing interpolation, no extrapolation beyond that. And 10.25 for our Gatorade. Orange soda. By the way, this was poured in the cup, back and forth in cups to get rid of the carbonation. I think you can think about why that's the case. If I did this with a freshly opened bottle of soda, I'd be having all kinds of bubbles in here, and that would obviously throw off. Actually, as it is, I got little bubbles off the bottom there, but that would throw off the reading. I'd have a bunch of air mix in. That would definitely throw up. Which direction would it throw it off? That's a good thing to consider. Here's my orange soda. Obviously, those bubbles would be taking the place of solution and making the mass come out too low. And I did it again. Forgot to zero it. That's okay. We'll do a little subtraction here. And otherwise, my orange soda is going to be off the charts because it comes out to be 20. The scale is now saying 20.75. Oh, that's easy. 10.50 for the orange soda. What's your thinking? Coke. More or less sugar content than the orange soda? Let's find out. Zero it. Bring that Coke up. Whoops, wrong one. Okay, there's your Coke. We're going to add that. Most students predict Coke would be a higher sugar content than orange soda. I think just having the orange associated with it, that's a fruit, makes it healthy, therefore less sugar. But right now, 10.42, yeah, Coke is actually not as sugary as orange soda. And finally, grape juice. That's the healthiest, right? There's more to consider than just the sugar content, but here we go with the grape juice. Oh, it's almost there. There we go. Oop, caught it that time. And what are we thinking for the grape juice? Right around the same as Gatorade? No, up to by the beverages of the Coke, orange soda? Let's find out. Even if it says 100% grape juice, which this says, it doesn't mean it doesn't have sugar in it. Where do you think that sugar comes from anyway? Fruit. Okay, you ready for this? Grape juice, 10.64. So, the correct ranking of these, if you want, by lowest to highest, Gatorade, Coke, orange soda, and then grape juice is the highest sugar content. Now, you can do better than that. Why do we generate this graph? Because now we can take, let's use just Coke as an example. 10.42 means Coke's density is 1.042 grams per milliliter. So I'm going to go back to my graph here, go to 1.042, over to our standard line, and down, and get that Coke is about 11.5% sugar by mass. Okay? We could do that with each of the beverages and find their relative percents. How can we compare that to what's on the label? Okay?